Okay guys, last lesson in our Advanced Chemical Reactions unit is on oxidation reduction reactions. Okay, oxidation reduction, big terms. So if you're looking at your PowerPoint, the biggest thing on there says you got to remember what electronegativity is. Electronegativity is a measure of how tightly your atoms are holding onto their electrons. We talked about your periodic table. Let's see if I can draw a little one here. Okay, and we talked about the trend, where we have high electronegativity down to low and high down to low. Has to do with size, has to do with shielding, all that good stuff. We also talked about how things over here and things over here have very large electronegativity differences, and they form ionic bonds. This is the Chick-fil-A milkshake. I want the milkshake. Okay, there's me. I want the milkshake. You could really care less. You don't want the milkshake, so guess who gets it? That's right, your favorite teacher. That's an ionic bond. It is transferring electrons. So given that 2 seconds of background information, if you think about the combination of sodium, which is a metal over on the left side of the periodic table, and chlorine, which is a nonmetal over on the right, you know that they combine to make salt, sodium chloride. But what's really happening is sodium is taking its electron off and giving it to chlorine. That's what's forming their bond. So you can also think about this reaction as these sodiums and these chlorines are forming really these two ions that are joined together. Sodium is now short an electron, chlorine now has an extra, but they're both more stable, so they're hanging out together because they're more stable. So that leads us, and we're going to focus on this reaction. I'm just going to rewrite it on a new page. If we're looking at that reaction we just made, 2 sodiums plus a diatomic chlorine makes 2 combinations of Na plus and Cl minus, there's really 2 different things happening here. Okay, this is an oxidation reduction reaction. One of the things that's happening is your 2 sodiums are becoming positive ions. That is because they are losing their electrons, and that's what we call an oxidation reaction. So the part of this whole green reaction up top where sodium becomes a sodium ion, that's an oxidation reaction. The other thing that's happening is your diatomic chlorine is ending up producing 2 chlorine ions. You can kind of see where we got that from your green reaction. By forming a chlorine ion, it is gaining electrons, and that is called a reduction. Now, I know that seems contrary, where gaining electrons is a reduction, but you got to remember that electrons are negative. If that doesn't work for you, here's my trick. You need to remember oil rig. Okay, oil rig. What that means is oxidation, that's my O, is loss. There's the oil part. Reduction is gain. That's the rig part. And if you try to write it another way, the word that you get is oig-ril, and the last time I, thought about it, that makes 0 sense. So oxidation is a loss of electrons, reduction is a gain. So the kind of logical question that follows is, well, how do I know what the heck is happening? The way you know is we use what's called oxidation numbers. And there are a ton of rules surrounding oxidation numbers, which you will see on your worksheet. Essentially, though, an oxidation number is how many electrons were added or removed. That's really what's happening. If I have an oxidation number of -1, that's meaning that I gained an electron. Okay, that's what that means. Lots of times, it's the charge something is going to have if it's an ion. So the way we assign oxidation numbers is we always start with things that are by themselves. Okay, so things that are not in compounds is who you want to start with. The easiest ones are the ones that are not just sitting there. O2. Okay, if you happen to see Fe, they're just sitting there. They're by themselves, they're neutral, they're stable, that's it. Those get an oxidation number of 0. They haven't gained anything, they haven't lost anything, they're pretty much just sitting there nice and neutral. Okay, the other ones that we look at are ones that have a charge. Let's say we had a zinc ion included, or we had a fluorine ion in there. These guys are pretty simple to assign oxidation numbers because it's their charge. Zinc is a +2. He's got to lose 2 electrons. Fluorine is a -1. He's got to gain. So when you're assigning oxidation numbers, the oxidation number of a neutral element by itself, and yes, a diatomic counts as by itself, is 0. An ion by itself is simply its charge. Easy. Okay? And I'm going to tell you what we're going to do with this in a second, but stick with assigning the numbers first. The next thing we assign are your compounds. Now, when you assign compounds, you have to remember some basic rules. All of your neutral compounds add up to 0. Okay, in fact, I won't put an equal, I'll put add up to 0, just like when we were doing ionic bonding earlier this year. If you have a charge on a compound, then the parts have to add up to that charge. Add up to charge. For example, if I give you NaCl, that means the Na plus the Cl have to equal 0. If I give you NO3 with a -1 charge, the nitrogen plus your 3 oxygens, O plus O plus O, those have to all equal up to -1. So when you're looking at compounds, you got to think of the parts and what they're going to add up to. That's the first thing you got to figure out. So then you have to decide which one gets a number first. Okay, which one are you actually going to assign? So the rule of thumb here is you assign the most electronegative atom first. So you got to go back to the trend on the periodic table. When you think about that trend on the periodic table, the highest electronegativity is right up there. So you're going to start, if you have an ionic compound, it's easy. It'll be something here and something here. Assign this guy's number based on its ion charge on the periodic table, and then you just worry about this guy making it add up correctly. For example, if you were doing sodium chloride, chlorine is by far the most electronegative. So I know sodium plus chlorine has to equal 0 because it's a neutral compound. I know that chlorine is -1 because that's what column it's in over here on the periodic table. So then I know my sodium, in order for the whole thing to equal 0, my sodium has to have an oxidation number of +1. You'll notice on the PowerPoint it mentions that hydrogen is usually a +1 and oxygen is usually a -2. But please keep in mind that's not always the case. Most of the time it's the case, but not always. So here's what we do with oxidation numbers. You've got a whole worksheet where you can practice assigning the numbers. You'll notice there's some I gave you. But what we use oxidation numbers for is to determine whether or not something is a redox reaction. Oxidation reduction is a mouthful. Okay, so instead of saying an oxidation reduction reaction every single time, usually people just abbreviate it as redox. So we're going to take the equation H3O plus Zn yields diatomic hydrogen plus water plus a zinc ion. And we are going to assign oxidation numbers. So we'll start with our uncombined just like we did earlier. Zinc is an uncombined. So if I look at this zinc right here, there's no charge on him. He's by himself. He's a 0. If I look at my hydrogen right here, there's no charge. He's by himself. He's a 0. If I look at my zinc over here, he's by himself, but he has a charge, and I know his oxidation number has to be his charge, which is +2. Then I need to look at my compounds. Okay, as I look at my compounds, let me switch my color. We'll start with H3O plus. Okay, H3O plus, I'm going to come down here at the bottom. I know I have to have 3 hydrogens plus an oxygen, and it has to be equal to +1. That's kind of what it's giving me right here. So if I assign the most electronegative one first, that's obviously my oxygen. So I'm going to give it its ion charge, which is a -2. That's what column it's in. And then this becomes a simple algebra problem. Scroll up just a hair. Okay, I get 3H is equal to 3, and then each H is a positive. That's not a number sign, that's a plus, I swear, +1. So in this case, my hydrogen is +1, my oxygen's -2. Now I'm going to come over here to my H2O, and I know this looks like H2O plus. I put my plus sign a little high, so that's a little better. When I look at my H2O right here, it's neutral. There's no charge. So 2 H's plus my oxygen have to be equal to 0. And I'm just going to draw my 0 with a line through it so you can tell the difference between it and my O's. So again, I assign the most electronegative first. That's oxygen. Oxygen's a -2, so then it becomes an algebra problem. 2 hydrogens equal 2. Each hydrogen equals +1. So hydrogen's a +1, oxygen's a -2. To decide if it's a redox reaction, I want to see if any of my oxidation numbers change. So if I look at my hydrogen, hydrogen here is a +1, hydrogen here is a 0. Now it's a +1 here, so that doesn't change, but it totally changes from +1 to 0. So I'm going to make a little note of that, and I'm just going to do this here in the middle because I have a little bit of space, so we'll just kind of cordon off a little spot. So my hydrogen goes from +1 to 0. That's what happens to its oxidation number. So now look at my oxygen. My oxygen's a -2 here, it's a -2 here. Nothing changes. I'm not worried about him. Now look at my zinc. My zinc is a 0 here, he's a +2 here. He changed. So zinc went from 0 to +2. So with zinc going from 0 to +2, hydrogen goes from +1 to 0, I know it's a redox reaction. I know that there has been a change in oxidation numbers, electrons have moved somewhere. So then I have to think about which one is which, okay? What's happening with this hydrogen is it goes from a +1 charge to a 0. The oxidation number is going down. That means I have gained electrons, and that means my hydrogen has been reduced. Okay? And again, you have to remember, I'm gaining negative things, so it's being reduced. With my zinc, I'm going from a 0 to a +2. So clearly, I have lost electrons in order for my charge to go up, so that is my oxidation reaction. So this entire reaction is considered a redox because I have one element who has been reduced. Let me switch colors again. I have one element that's been reduced, my hydrogen, and another element that has been oxidized. That's my zinc. That's a very, very brief overview of oxidation numbers and reactions. But one last thing I want to point out to you, and I put this on your PowerPoint, your oxidation numbers have a very strong connection to electron configurations. If you look at something that is 1s2, 2s2, 2p3, you know that that has 5 valence electrons. Okay, your valence are going to be the ones in level 2. 5 valence electrons means I'm going to have an oxidation number of -3, because in order to become stable, I need 8 total valence electrons, so that 5 plus 3, that's going to make me stable. If I had an electron configuration of 1s2, 2s2, 2p6, 3s1, I have 1 valence electron. And just like we talked about, sure, you could have a +7 oxidation number, but that's probably not very likely, okay? That's going to be kind of a big pain, okay? More likely, or I'm sorry, not a +7. I could have a -7 oxidation number. I could gain 7 more electrons, but more likely than that, I'm going to lose 1, and I'll have a +1 oxidation number. There are some periodic tables that list all of the options. Both of these really are options, just like there really is another option up top. Up top, I really could have a +5. Sometimes you'll see other options to get half full orbitals and full orbitals, but usually you will see a connection where you have them adding up to equal 8, or you'll have them dropping back down, whichever one is simpler.